Okay, so this video is going to be talking about our 3D support reactions, frame, machine problems, things like that. And what I mean with that is this question 3 on the 2019 exam. So this is the rod with its support reactions. And this question 4 on the 2018 exam, which is this hanging sign. It's got 2 cables, etc. I'm not going to do either of these problems completely all the way through, but I'm going to talk about what the setup would be and then how you'd go about solving them, just because these are a little more in-depth and this will vary a lot depending on what problem you're given. So what matters more is the setup than how I actually go through and solve each of these. So I'm going to start with this problem in the 2018 exam with this hanging sign. And the biggest thing is one, knowing what each support reaction means. So right in the description of this problem, they tell you that you have a ball and socket joint at A, and then obviously we got the 2 cables. So the question we have to ask ourselves is, what is a ball and socket joint and what are the support reactions? So there should be a chart from the textbook, a chart that you've talked about in class that'll give you like basically a list of what a support reaction, like what the support reaction is and then what its actual components are. So for example, like you should be able to look at the chart, and if they gave you something that said we have a journal bearing, something along those lines, you should be able to say, oh, okay, I know support reactions from that. For ball and socket joints, you just have 3 forces. So the way that I would do it is I would just say, okay, that means I have an AZ, an AY, and an AX that just run right along the axes. The reason that I draw them in these directions, if you notice, is they're all positive. And that's not necessary, but for me, that makes it easier when I then end up wanting to do summation of forces because they're all positive. I don't have to worry about them being negative. The other forces that we're going to need to take into account here are, one, the weight of the sign, because they tell you, hey, it weighs 270 pounds. And the last thing that we're going to have to take into consideration is the cables, right? And this is where a little more setup is needed. So I'm going to go into the whiteboard feature on here to be able to talk about that. So there we've got the whiteboard shared. So if I just do a quick sketch of what that board looked like, here's the board, something on those lines. And what we had is we had one tension that was going this way, which we'll call BD. And we had one tension kind of going this way, which we'll call CE for reference. And what we know about forces more generally is that they can be defined with a magnitude and a unit vector, right? Because forces are vectors, which means they have both magnitude and direction. So in a general sense, we should be able to say that the vector F is equal to the magnitude of F times the unit vector. So if we're thinking about that in terms of BD, we should be able to say that the vector BD is equal to the magnitude of BD times the unit vector BD, right? So in this case, when we think about the unit vector for BD, we're going to get it from the geometry that's on the actual problem. So if you follow along on the problem, the position vector for BD is -8 I hat plus 4 j hat minus 8 k hat. So when we get the magnitude of that, which is necessary to find the actual unit vector, we'll see that it's just 12, right? Because we take the square root of 8 squared plus 4 squared plus 8 squared, right? And then from here to do the actual unit vector work, the unit vector BD is going to be equal to the vector, the position vector, divided by the magnitude of the position vector. So in that case, I left mine in fractions, but I got -2/3 I hat plus 1/3 j hat plus, minus 2/3 k hat. And what I can then say is the fact that BD is going to be equal to the magnitude of BD times this vector, right? And the reason that that is actually useful in the problem is because when we go and we try and use our summation of moments or our summation of forces, instead of having 3 unknowns, which is like Bx, By, and Bz, we now have one unknown, right? Because we're able to relate the three components of BD using its unit vector. So we'll go through a similar process for CE. So I'm just going to get a new page. So we're looking at CE being equal to the magnitude of CE times the unit vector for CE. So for this, I have a position vector for CE as -8 I hat plus 3 j hat plus 2 k hat. So you can end up getting a unit vector same way as before. This one ends up being not nice fractions, it ends up being decimal. So I have something along the lines of -0.912 I hat plus 0.342 j hat plus 0.228 k hat. So we know that we can then express CE as being the magnitude of CE times this unit vector, right? So where we go from here is then kind of the big question. So if I switch back to sharing, if I stop sharing this, and then I go in and reshare the exam, something that we can think about is the fact that, yes, we don't know any of the support reactions at A, right? And they're not related to each other either. It's not like there's no relationship that says AX is somehow proportional to AY. Right? It's just not true. So if we were able to remove these, that would make it a lot easier for us to figure out everything else. So for example, the tensions in the rope, and then use those to get AX, AY, and AZ. The easiest way to do that is to take a moment. So if we think about the weight pointing down, each of the tension forces can be split into their three components, right? So what I would basically have is I would have a BY, a BZ, and a BX, right? And I would have the exact same thing over at E, so an EY, an EZ, and an EX. Doesn't matter what direction. They'll end up being either positive or negative along those lines. What I would basically do is I would say, okay, let me take a moment about, for example, the z-axis. So if I'm considering the z-axis to take my moment about, not all of these forces are actually going to create a moment about the z-axis. So you have to imagine that you're basically standing on the z-axis. Which of these forces are actually going to rotate around you? The weight will, that's obvious. And then both of these y forces will, right? But none of the other ones will, if we really think about it, right? Because the x forces run right through the axis, right? Those will run straight through. Okay, that makes sense. They don't create a moment. But with the z components, they're never turning around the z-axis, right? Yes, they would turn about a y-axis if we took a moment about that, but they're not turning about the z-axis. So that means if we think about writing out the moment about the z-axis, the unknowns that we would have is the weight, which we actually know. It's not really an unknown. And we would have by or bdy, depending on how you want to write it, and cey, right? So what that means is that if we do the same thing, so that's one equation, two unknowns, so that's not helpful yet. But if we do the same thing, but instead we take the moment about the y-axis, a little bit like I was talking about, we should then be able to get another equation similar to this one, where we have more or less BD and CE as our unknowns. Two equations, two unknowns, boom, we know how to solve that. And from there, once I know the two tension forces, I would then say, oh, okay, now let me use summation of forces in the x, y, and z directions to figure out my AX, AY, and AC. Okay. So hopefully that made sense. You can let me know if you have questions on that. So the other problem that I want to just talk about is a problem from the 2019 exam. So this is a similar thing where the first thing I want to do is think about what my free body diagram is going to look like. So once again, we have another ball and socket joint, which means we're going to have an A, in this case it's AZ pointing upwards, AX, and a Y.
tension forces are relatively straightforward because they run right along the cable, right? So you can just call this T, call this BC, it doesn't really matter. And then the last force that we have to contend with is the fact that there's a normal force from B being at the wall, right? So the question is, how does this normal force act? So a mistake that some students will make is they'll say, oh, the normal force acts along the rod. That is not true. Normal force just acts straight out from the wall. So what this normal force is it basically just acts right along the x-axis, right? So if we're thinking about normal force as a vector, it's just going to be the magnitude times I hat. There's going to be 0 j hat, 0 k hat, right? And then what we know about the tension is the fact that this tension only has a y component and a z component, right? Because it's not moving in the x direction at all. This is the tension. So that also makes it easy for us to basically just want to use a summation of forces. The only force that I didn't draw on here is the fact that they tell you that this rod has a weight, right? It's got a weight of 25 kilograms. So we know that because it's uniform, it's just going to act right in its midpoint. So one of the things that could be tricky about this problem, depending on if you identify it, is where that midpoint actually is in terms of its position on the rod. So it's just going to be kind of right smack in the middle. So its actual point would be half of this distance, half of this distance, half of this distance. We could draw triangles and go through like that. So there's technically a triangle that looks like this, where it's in the middle of the hypotenuse, and we can figure out from there. But that's the biggest point, knowing where that force acts. In terms of other things to look out for in this problem, once again, moments are going to be helpful, like they usually are in these 3D problems, because if we need to, and we want to look and we want to take a moment about A, that's going to remove a good majority of our unknowns and could leave us with a problem that's a bit easier to solve. I think force reactions would also serve you well in this case. And by force reactions, I mean just summation of forces in, for example, Z, summation of forces in Y. I think those can end up being really useful in this problem as well, but I think you'll need moments still in some aspects. So that covers the main points I have about these problems, but once again, just important points to reiterate. Knowing if you're told a certain support reaction, so if you're told ball and socket joint, knowing what that actually looks like in terms of reaction forces. And then when you're doing a problem like this, you just need to be careful. So you have to make sure you realize that, hey, this rod has mass in this case, because a lot of the problems that we talked about the homework, we assumed massless, so we didn't have to worry about it. The other thing that we have to be careful about is knowing how things are related. So being careful that we're not trying to say that, for example, somehow this A, Z, AX, and AY were related, because in this case, they're not. But forces that we could say are related is these tension forces, right? So if we call the overall force T, TZ and TY are related. So knowing that versus knowing the A's aren't, that's an important thing to be able to note. And then from there, it's mostly just being able to use your summation of moments, summation of forces, and trying to understand, hey, what point can I take the moment around where it's going to be most helpful to me? Those are what I would say are the big kind of tips and tricks in order to solve these kinds of problems.